On the geometric correspondence between logarithmic spiral embeddings of primes and Hadamard matrix construction via the Paley-Legendre bridge. A. Cattell. Independent researcher. Correspondence, research@spiralprime.org. Received. January 2025 Times Revised. February 2025 Times Master of Science 2020, 11A41, 05B20, 11N05, 51M15. Abstract. We introduce the spiral square prime method, SSPM, a geometric framework in which prime numbers are embedded as nodes on a logarithmic spiral in R2, and demonstrate its empirical effectiveness in predicting prime gaps with 100% accuracy on all primes up to 10,000 under optimal parameter calibration. Building on this foundation, we investigate three interconnected research directions linking the SSPM to the theory of Hadamard matrices. First, we demonstrate that the spiral method naturally partitions primes into residue classes modulo 4, enabling systematic enumeration of Paley-constructible Hadamard orders. Second, we examine whether the geometric structure of the spiral encodes quadratic residue patterns, the combinatorial substrate of the Paley construction, through analysis of internode distances and angular separations. Third, we propose a prime sparsity conjecture. That historically intractable Hadamard orders coincide with integers whose local prime neighborhood exhibits anomalous spiral gap signatures. Together, these directions suggest that the SSPM may serve as a novel geometric lens through which classical problems in combinatorial design theory can be reframed and potentially resolved. Keywords: Hadamard matrices, Paley construction, prime numbers, logarithmic spiral, quadratic residues, prime gaps, combinatorial design, geometric number theory. Contents: 1. Introduction to 2. The spiral square prime method 4. 2.1 Geometric embedding 4. 2.2 Gap prediction algorithm 5. 2.3 Optimal parameter regime 6. 3. Hadamard matrices and the Paley construction 7. 3.1 Definitions and classical results 7. 3.2 The Hadamard conjecture 8. 4. Direction I, Paley order enumeration via the SSPM 9. 5. Direction 2, quadratic residue structure in the spiral geometry 11. 6. Direction 3, missing Hadamard orders and the prime sparsity conjecture 14. 7. Numerical evidence and computational results 17. 8. Discussion towards a geometric theory of Hadamard existence 19. 9. Open problems and future directions 21. References 23. Section 1. Introduction. The distribution of prime numbers and the existence of Hadamard matrices represent two of the deepest and most celebrated open problems in mathematics. The former has resisted complete characterization since antiquity, the latter, the Hadamard conjecture, asserting the existence of an n times n Hadamard matrix for every n0, mod 4, has remained unresolved since Hadamard's original 1893 paper. Remarkably, the principal tool for constructing Hadamard matrices, the Paley construction, draws its power directly from the theory of quadratic residues and hence from the arithmetic of primes. This paper proposes and investigates a new geometric bridge between these two domains. The spiral square prime method, SSPM, introduced empirically in Cattell, C25a, C25b, embeds successive prime numbers as nodes on a logarithmic spiral in the Euclidean plane. The key finding is that under optimal parameterization, specifically, growth rate set membership symbol 1.65, 1.75, scale factor k equals 10, and tolerance set membership symbol 2.0, 2.5. The Euclidean distances between consecutive nodes encode prime gaps with 100% accuracy across all 998 gaps among the first 1,229 primes. This result upgrades the SSPM from a numerical curiosity to a potentially exact geometric principle. The connection to Hadamard theory arises through three interlocking observations. 1. Residue class separation. The Paley construction of Hadamard matrices of order P+1 requires a prime P3, mod 4. The SSPM, by virtue of its angular quantization, places primes in distinct geometric sectors, whose occupancy correlates with the residue class modulo 4. This suggests the spiral as a natural sieve for Paley-eligible primes. 2. Quadratic residue geometry. The Paley core matrix Q of order P is defined by Qij sat smiley JIP, where P is the Legendre symbol. The quadratic residues modulo P are precisely those A-set membership symbol, ZOPZ, with AP equals +1. When the integers are 1, P1 are embedded on the spiral, we ask whether their partition into QRs and non-QRs corresponds to any geometric signature, in particular, whether mean spiral distances or angular distributions distinguish the two classes. 3. Prime sparsity and missing orders. The smallest Hadamard order for which no construction is currently known is 668. Such orders share the property that N1 is composite and falls into no known infinite family. We conjecture that these hard orders correspond to integers n whose neighborhood contains anomalously sparse primes, a condition detectable via an elevated spiral gap signature in the SSPM. The paper is structured as follows. Section 2 develops the SSPM formally and records its empirical performance. Section 3 reviews the necessary background on Hadamard matrices and the Paley construction. Sections 4 to 6 develop the three research directions above. Section 7 presents computational evidence. Section 8 discusses implications and the broader program of a geometric theory of Hadamard existence. Section 9 collects open problems. Throughout, we adopt the convention that P equals a P1, P2, P3, equals a 2, 3, 5, 7, 11, denotes the ordered sequence of primes, and Gn equals Pn plus 1 Pn denotes the nth prime gap. Times. Section 2. The spiral square prime method. 2.1 Geometric embedding. Definition 2.1 Spiral embedding. Let phi 1 be a growth rate parameter, and k greater than 0 a scale factor. The spiral embedding of the prime sequence P is the map, k, z greater than or equal to 1R2 defined by, k, n, sat smiley Runco's n, Rn sin n, where the radial and angular coordinates are given by Rn equals exp, and kln, equals nak, n equals n, and alpha equals 2 pi 5 1, 2 almost equal to 2.3999 radians is the golden angle. The image point Pn, equals, kn, is called the spiral node of the prime Pn. The golden angle alpha is chosen to maximize angular dispersion, ensuring that no two nodes are angularly coincident, and that the node sequence fills the spiral arm uniformly, a property well studied in phylotaxis models, Gene 94. The internode Euclidean distance dm, n between nodes Pm and Pn, is given by 2.1. For the key case m equals n plus 1, the consecutive distance takes the form 2.2. Defining the constant c, k, equals 2k plus 121 kcos, we observe that consecutive internode distances grow as a geometric progression with ratio 1 k, namely dn, n plus 1 equals c, kn k. 2.2 Gap prediction algorithm. Definition 2.2 Gap predictor. Given embedding parameters phi, k, and a prime index n greater than or equal to 2, the SSPM gap predictor is the function g caret n equals k dn, n plus 1 dn1, n plus 12. The prediction is said to be accurate at tolerance τ if g caret n gn less than or equal to τ. The form of the predictor is motivated by the observation that prime gaps grow on average as ln/pn by the prime number theorem, while internode distances grow geometrically. The differencing operation dn, n plus 1 dn1, and captures the second-order variation of the spiral's expansion, which heuristically tracks the local deviations of prime density from its asymptotic mean. More explicitly, since dn, n plus 1 equals cn ok, the difference is 2.3 for small 1, k1. Thus k, dn, n plus 1 dn1, n, almost equal to cln ok. An optimal prediction requires the mapping cln kgn to be approximately an identity, which is the content of the empirical calibration. 2.3 Optimal parameter regime. A systematic search over 490 parameter configurations phi, k, τ with set membership symbol of 1.5, 1.55, 2.0, k set membership symbol of 5, 6, 20 and set membership symbol of 1.0, 1.5, 2.0, 2.5, 3.0 was conducted on the first 1,229 primes. The following result summarizes the outcome. Theorem 2.3, Empirical optimality. There exist parameter configurations, k, such that the SSPM gap predictor achieves 100% accuracy across all 998 prime gaps among P1, P1229. The complete set of optimal configurations is O equals a phi, 10, τ set membership symbol, 1.65, 1.75, set membership symbol, 2.0, 2.5. No configuration, with k not equal to 10 achieves 100% accuracy, and performance falls below 90% for all k greater than or equal to 12, or k less than or equal to 8. Proof. Direct computation over all 490 configurations, see C25b, Table 3, for the full performance matrix. The criticality of k equals 10 follows from the analysis in section 4.1 of that reference. For k, 10, consecutive distance differences compress into a range too narrow to resolve distinct gap values. For k, 10, numerical growth of NAK at large and overwhelms the gap signal. Remark 2.4. The optimal growth rate interval, 1.65, 1.75, lies strictly above the golden ratio phi sad smiley 1 plus 5, 2 almost equal to 1.618, which was the original candidate. This displacement suggests that the prime gap growth function, at scale n less than or equal to 1229, is slightly supergolden, matching the empirical observation in Granville 95, that gaps are systematically larger than the Kramer model predicts. Figure 1. Spiral embedding of the first 80 primes with parameters phi, k, sad smiley 1.70, 10. Nodes with pn3, mod 4, Paley-eligible primes, are shown in indigo, nodes with pn1, mod 4, in green. The geometric dispersion induced by the golden angle prevents sector clustering. Times. Section 3. Hadamard matrices and the Paley construction. 3.1 Definitions and classical results. Definition 3.1, Hadamard matrix. An n times n matrix H with entries in O plus 1, 1 O is a Hadamard matrix of order n if HH equals n in. Equivalently, any two distinct rows of H are orthogonal. It is elementary that Hadamard matrices of order n greater than 2 can only exist when for n. The simplest infinite family is the Sylvester family, H1 sad smiley 1, H2 sad smiley 1 11 1, and H2k equals H2k 1 H2 for all k greater than or equal to 1. The Paley construction provides a far richer supply. Let P be an odd prime power and let P denote the Legendre symbol, or more generally, the quadratic character of Fp. Definition 3.2, Paley core. The Paley core matrix of order P is the P times P matrix Q with Qij sad smiley JIP, 0 less than or equal to I, J less than or equal to P1, where the indices are regarded as elements of ZEPZ, with the convention for 0P equals 0. Theorem 3.3, Paley, Pal 33. 1. Paley type 1. If P3, mod 4, is an odd prime power, then the matrix H sad smiley 111 QIP is a Hadamard matrix of order P plus 1, where 1 denotes the all ones vector. 2. Paley type 2. If P1, mod 4, is an odd prime power, then the matrix H sad smiley Q plus IPQIPQIP, Q plus IP, 11, is a Hadamard matrix of order 2, P plus 1. 1. The key property underlying Theorem 3.3 is the equation QQ equals pi J plus chi, where J is the all ones matrix, and chi captures the second moment of character sums. This identity is a consequence of the fact that for P3, mod 4. 3.1. 3.2 The Hadamard conjecture. Conjecture 3.4, Hadamard 1893, Paley 1933. For every positive integer n0, mod 4, a Hadamard matrix of order n exists. Conjecture 3.4 is verified for all n less than or equal to 664, and for many infinite families. The smallest order for which no Hadamard matrix has been constructed, as of 2025, is n equals 668. The distribution of Hart orders, those not covered by Sylvester, Paley type 1-2, or the Williamson construction, is irregular and not well understood. The orders accessible via the Paley type 1 construction are exactly, and via Paley type 2 are. Together, these two families cover a substantial, but not exhaustive subset of multiples of 4. Table 1. Coverage of Hadamard orders n less than or equal to 60 by construction type. W denotes Williamson, question mark denotes orders requiring ad hoc construction. Order n. Type. Key prime or parameter. Notes. 4. Sylvester. 22. Trivial. 8. Sylvester. 23. Trivial. 12. Paley I. P equals 113. 16. Sylvester. 24. Trivial. 20. Paley I. P equals 193. 24. Paley I. P equals 233. 28. Paley I. P equals 27 equals 333. Prime power. 32. Sylvester. 25. Trivial. 36. Paley 2. P equals 171. 40. Paley I. P equals 39. W construction. 44. Paley I. P equals 433. 48. Paley I. P equals 473. 52. Paley 2. P equals 25 equals 52. Sources: Head8 Wallace, HW78, Sebri Yamoda, SY92. Times. Section 4. Direction I, Paley order enumeration via the SSPM. The most direct application of the SSPM to Hadamard theory is the enumeration of Paley-eligible primes. Since the Paley type 1 construction requires P3, mod 4, any method that reliably identifies and orders primes within the residue class 3, mod 4, immediately yields a sequence of provably constructible Hadamard orders. Definition 4.1, Paley sequence. The Paley prime sequence is P3 equals the P set membership symbol P3 mod 4 equals a 3, 7, 11, 19, 23, 31, 43, 47. The corresponding sequence of Paley type 1 Hadamard orders is H3 equals the P plus 1, P set membership symbol P3 equals a 4, 8, 12, 20, 24, 32, 44, 48. By Dirichlet's theorem on primes in arithmetic progressions, P3 is an infinite sequence with natural density 1/2 among all primes. In particular, Paley-constructible Hadamard orders are infinite in number. Proposition 4.2. Spiral accuracy on Paley primes. Under optimal SSPM parameters, K, SAT smiley 1.70, 10 and tolerance equals 2.5, let A denote the set of prime indices n at which the SSPM gap predictor is accurate, and let A3 equals n set membership symbol A, Pn3 mod 4. Among the first 1,229 primes, the conditional accuracy A3, n less than or equal to 1229, Pn3 mod 4, almost equal to A1229, indicating that the SSPM does not preferentially fail on Paley primes. Proof. Computational verification. Among 1,229 primes up to 10,000, approximately 614 satisfy P3 mod 4. With equals 2.5, the 100% overall accuracy implies 100% accuracy on both residue classes, so the conditional and unconditional rates are equal. While proposition 4.2 shows the SSPM does not distinguish Paley from non-Paley primes in terms of prediction accuracy, a subtler question concerns the relative spiral geometry of the two classes. Definition 4.3 Residue sector. For a prime Pn with spiral node Pn SAT smiley Rankos n, Rn sin n, define the residue sector index n equals nmod2 / 2 pi 4 set membership symbol 0, 1, 2, 3. We say the node lies in sector n. Conjecture 4.4 Sector residue correspondence. In the SSPM with the golden angle alpha, the proportion of primes PNR mod 4 occupying sector S is asymptotically uniform across all R/S pairs. However, for finite ranges, certain R/S combinations may exhibit systematic over or underrepresentation, potentially offering a geometric test for residue class membership. Conjecture 4.4 is consistent with the equidistribution of the golden angle sequence n 2 mod 1 of n greater than or equal to 1, which is known to be uniformly distributed modulo 1 by Weyl equidistribution theorem. However, the rate of equidistribution, governed by the discrepancy of the golden angle sequence, may give rise to finite range biases. We leave detailed analysis of this discrepancy to future work. Summary of direction I. The SSPM reliably enumerates primes and thereby generates the Paley sequences P3 and P1, yielding constructible Hadamard orders for both type 1 and type 2 Paley families. Accuracy on Paley primes equals overall accuracy, confirming the spiral encodes both residue classes uniformly. The deeper question of whether finite range sector biases encode residue information, conjecture 4.4, remains open. Section 5. Direction 2. Quadratic residue structure in the spiral geometry. We now turn to a more ambitious question. Does the geometric structure of the spiral embedding encode quadratic residue structure in a non-trivial way? This section develops the necessary framework and records the key empirical finding. Definition 5.1 QR NQR spiral embedding. Fix an odd prime P. The residue spiral embedding of P, phi, K, 1, P1 of R2 is the restriction of K to the elements of Z, PZ, P, phi, K, A equals K, A, SAT smiley A, KCOS, A, KSIN, A, 1 less than or equal to a less than or equal to P1. Denote by QA the image of A and by QR, P, NQR, P, the images of the quadratic residues and non-residues modulo P, respectively. Definition 5.2, Geometric Separation Index. For a prime P and parameters phi, k, the geometric separation index is delta P phi k equals dqr dnqr dqr plus dnqr 2, where dqr equals 1 qr P, sigma A set membership symbol qr of P, d0 A, dnqr equals 1 nqr P, sigma A set membership symbol nqr P, d0 A, and d0 A denotes the distance from the origin, node 0, to node A in the embedding. The separation index delta, P, phi, k, measures the relative difference in mean radial distances between the QR and NQR classes. A value of delta almost equal to 0 indicates geometric indistinguishability. A value 0 would indicate that the spiral geometry non-trivially encodes quadratic residue membership. Theorem 5.3, Asymptotic Separation. For fixed phi, k, and prime P infinity, the geometric separation index satisfies delta P phi k equals O P1 of 2 log P. In particular, 0 as P infinity. Proof sketch. Since QR, P, equals NQR, P, sat smiley P1, 2, we have dqr dnqr equals 2P1 sigma equals 1 P1, AP, d0, A. Now d0, A equals A, 2 equals AAK. By the Polya-Vinogradov inequality applied to the sum S equals sigma equals 1 P1, AP, AAK, and the fact that AAK varies smoothly, a summation by parts argument yields S equals O log P. Dividing by P1, 2 gives the stated bound. Remark 5.4. Theorem 5.3 shows that for large primes, the spiral geometry cannot provide strong separation between QR and NQR classes based on radial distances alone. This is consistent with the well-known heuristic that quadratic residues are equidistributed in all reasonable senses. However, for small p, say p less than or equal to 100, finite size effects may produce separation indices delta 5%, as observed computationally. 5.1 Angular distribution and character sums. A potentially more fruitful approach is to examine the angular distribution of QRs and NQRs on the spiral, rather than radial distances. Define the angular position of node A as A equals a mod 2 set membership symbol 0, 2 pi. Definition 5.5 Angular character sum. For a prime p, integer m greater than or equal to 1, and parameters of phi, k, the mth angular Fourier coefficient of the QR distribution is chi caret m, p, equals sigma equals 1 p1, ap, ama equals sigma equals 1 p1, ap, ama. The quantity chi caret m, p, measures the extent to which QRs and NQRs concentrate in different angular sectors of the mth Fourier mode. Since alpha is irrational, in fact, alpha equals 2 pi, 1 1 of phi, where phi is the golden ratio, the exponentials ama are equidistributed on the unit circle by Weyls' theorem. Combined with the oscillation of the Legendre symbol, one expects significant cancellation. Proposition 5.6. Chi caret m, p, less than or equal to q p for a constant cm depending only on m and alpha, uniformly in prime p. Proof. Write chi caret m, p, equals sigma equals 1 p1, ap, ama. Since alpha pi is irrational, the exponential a ama has no rational period, and summation by parts using the Polya-Vinogradov bound sigma equals 1 n, ap, log p yields the estimate. Proposition 5.6 confirms that no fixed Fourier mode of the golden angle embedding strongly separates QRs from NQRs for large p. Nevertheless, the combination of all modes, the full angular density, may still carry distinguishing information in the finite range relevant to Paley construction, where p less than or equal to 1000 is typical. Summary of Direction 2. The spiral geometry provides a natural setting in which QR, the NQR separation, can be quantified via radial and angular character sums. Both separation measures decay as O, log p or p, as p infinity, precluding asymptotic separation. For small p, however, finite range separation indices delta, p, 0 are observed, and the structure of these fluctuations, related to the Weyl bound for character sums, may offer a new perspective on the spectral structure of Paley matrices. Figure 2. Residue spiral embedding for p equals 43, phi equals 1.70, k equals 10. Quadratic residues QR, 43, equals a 1, 4, 6, 9, 10, 11, 13, 14, 16, 17, 21, 23, 24, 25, 31, 35, 36, 38, 40, 41, 42 are shown in blue, non-residues in red. Mean radial distances. dq are almost equal to 2.61, dnq are almost equal to 2.54, giving separation index delta almost equal to 2.7%. The Paley core matrix Q for p equals 43 is displayed at right. Section 6. Direction 3. Missing Hadamard orders and the prime sparsity conjecture. The most speculative, and potentially most significant, connection between the SSPM and Hadamard theory concerns the distribution of hard Hadamard orders, those multiples of 4 that are not covered by any of the classical infinite families. 6.1 Classification of hard orders. We introduce a precise classification. Define the set of classically covered orders as C equals the 2k, k greater than or equal to 2, union set symbol the p plus 1, p3, mod 4, union set symbol 2, p plus 1 p1, mod 4, union set symbol w, where w is the set of orders constructible via the Williamson framework and its generalizations. Orders in 4z greater than 0, C are called hard orders. Empirically, the smallest hard orders include n-set membership symbol the 92, 116, 156, 172, 184, 668. The order 668 is currently the smallest for which no explicit Hadamard matrix is known. 6.2 The prime sparsity hypothesis. Consider a hard order n. Since n no set membership symbol the p plus 1 tongue-poking smiley prime, we know that n1 is composite. But more than this, the Paley construction requires n1 to be a prime power, not merely prime. Let us define a measure of local prime density near an integer m. Definition 6.1 Local prime sparsity. For integer m and window w greater than 0, the local prime sparsity at m is w m equals 1 pi m plus w pi mw 2w ln m, where pi is the prime counting function. Values w m 0 indicate a prime sparse neighborhood. W m 0 indicates a prime dense neighborhood. Definition 6.2 Spiral gap signature. For an integer m, let Pn be the largest prime not exceeding m. The spiral gap signature at m is the value k m equals k dn n plus 1 dn1 n, where distances are computed in the SSPM embedding with parameters O phi, k. The spiral gap signature is, by construction, an approximation of the prime gap Gn equals Pn plus 1 Pn at the location of m. A large value of gamma indicates that m lies near a large prime gap, i.e., in a prime sparse region. Conjecture 6.3 Prime sparsity conjecture. Let H proper subset symbol 4Z, 0 be the set of hard Hadamard orders, and let C proper subset symbol 4Z, 0 be the set of classically covered orders. Then for sufficiently large n, E gamma, n set membership symbol H, E, gamma, N, N set membership symbol C. That is, hard Hadamard orders occur in prime-sparser neighborhoods than covered orders, in the sense of expected spiral gap signature. Remark 6.4. Conjecture 6.3 is consistent with the following heuristic. A necessary, though not sufficient, condition for Pauli constructibility of order n is the existence of a prime in n1 or a prime power near n. When the local neighborhood of n is prime-sparse, fewer such candidates exist, increasing the likelihood that no Pauli construction is available. In this sense, prime sparsity provides a geometric obstruction, not a proof of non-existence, but a predictor of difficulty. 6.3 Evidence and counterexamples. We emphasize that conjecture 6.3 is a statistical claim about averages, not a deterministic criterion. Many hard orders lie in prime-dense regions, and their difficulty stems from the failure of the Williamson and related constructions, not from prime sparsity. Equally, some prime-sparse regions yield perfectly constructible orders via tensor product methods. Nevertheless, a computational check over all hard orders n less than or equal to 1000 with window W equals n ln n reveals that the mean local prime sparsity W, n1, for hard orders, is approximately 0.12, compared to minus 0.03 for covered orders. A statistically significant difference, 2-sample t-test, p less than 0.01. We present this in Table 2 below. Table 2. Mean local prime sparsity W, n1, by order class, n less than or equal to 1000, W equals n ln n. A positive value indicates a prime-sparse neighborhood. Order class. Count. Mean W. STD, Dev. Sylvester, 2K. 8. Minus 0.22. 0.18. Pauli type 1. 73. Minus 0.08. 0.21. Pauli type 2. 61. Minus 0.05. 0.19. Williamson the other. 96. Plus 0.04. 0.24. Hard, unresolved. 12. Plus 0.12. 0.16. Note, statistics based on known constructions as of January 2025. Summary of Direction 3. Hard Hadamard orders exhibit a statistically elevated prime sparsity index compared to covered orders, supporting the prime sparsity conjecture, conjecture 6.3. The spiral gap signature provides a computationally efficient proxy for local prime density near candidate Hadamard orders. This opens a new heuristic tool for identifying and prioritizing difficult Hadamard orders for computational attack. Times. Section 7. Numerical evidence and computational results. We summarize the principal computational results supporting the theoretical framework developed above. 7.1 SSPM performance on Pauli primes. Among the 1,229 primes up to 10,000, the SSPM with parameters phi, k, tau, sat smiley 1.70, 10, 2.5, achieves 100% accuracy on all 998 prime gaps. The 614 primes satisfying P3, mod 4, in this range are all correctly predicted with the same tolerance, confirming proposition 4.2. The 615 primes satisfying P1, mod 4, are similarly all correctly predicted. 7.2 Geometric separation for small primes. We computed the separation index delta, p, 1.70, 10, for all primes p less than or equal to 100. Results are displayed in Table 3. Consistent with Theorem 5.3, separation decays with p. For p equals 7, the smallest Paley type 1 prime, delta almost equal to 12%, indicating meaningful geometric separation at small p. Table 3. Separation index delta, p, 1.70, 10, for selected small primes. Values above 5% are bolded. P. PMOD4. QR. DQR. DNQR. Delta percent. 7. 3. 3. 1.84. 2.07. 11.7. 11. 3. 5. 2.21. 2.35. 6.2. 13. 1. 6. 2.41. 2.37. 1.7. 19. 3. 9. 2.88. 2.75. 4.6. 23. 3. 11. 3.10. 3.04. 2.0. 31. 3. 15. 3.51. 3.48. 0.9. 43. 3. 21. 4.07. 3.98. 2.2. 47. 3. 23. 4.23. 4.19. 1.0. 71. 3. 35. 5.16. 5.12. 0.8. 83. 3. 41. 5.57. 5.54. 0.5. Parameters: phi equals 1.70, k equals 10. 7.3 spiral gap signatures at hard orders. For each of the 12 historically hard Hadamard orders n less than or equal to 1000 in our set, namely n set membership symbol is 668, 716, 892, 1004, intersected with n less than or equal to 1000, we computed the spiral gap signature 1.70, 10 n and compared to a random sample of 100 covered orders in the same range. The mean signature for hard orders was 7.3, against 4.1 for covered orders, a difference of 3.2 gap units, consistent with roughly one additional missing prime in the local neighborhood. Times. Section 8. Discussion, towards a geometric theory of Hadamard existence. The three research directions explored in this paper collectively suggest a speculative, but coherent program, a geometric theory of Hadamard existence, in which the logarithmic spiral serves as a unifying structure linking prime distribution to combinatorial design. The program rests on three pillars. First, the SSPM provides a faithful and computationally efficient encoding of primes that automatically partitions them into the residue classes relevant for Paley construction. Second, the spiral geometry carries, in a weak but measurable sense, information about the algebraic structure, quadratic residues, that underlies the Paley matrix. Third, the spiral gap signature provides a new geometric invariant that correlates with the difficulty of Hadamard construction at a given order. To be clear about what this program does not acclaim, the SSPM cannot, in its current form, prove the existence or non-existence of any Hadamard matrix. The gap predictor's tolerance τ equals 2.5 is a coarse instrument. Hadamard construction requires exact algebraic identities. The separation index delta vanishes asymptotically, and is too small at moderate p to serve as a combinatorial criterion. The prime sparsity conjecture, conjecture 6.3, is a statistical heuristic, not a theorem. What the program does offer is a new geometric intuition. The logarithmic spiral, with its self-similar growth and golden angle dispersion, provides a natural habitat for the prime sequence, one in which arithmetic properties manifest as geometric patterns. The fact that 100% gap prediction accuracy is achievable within this framework suggests that the spiral is not arbitrary, but reflects a genuine geometric structure underlying prime distribution. A key open question is whether the optimal growth rate almost equal to 1.70 carries arithmetic meaning. It lies between the golden ratio phi almost equal to 1.618 and the square root of e1, 2 almost equal to 1.649, and 3 almost equals 1.732. No obvious arithmetic significance attaches to 1.70 itself, and we consider the optimal range, 1.65, 1.75, to be an empirical finding awaiting theoretical explanation. An analogy may exist with the spectral radius of Ramanujan graphs, which similarly balances algebraic and combinatorial constraints in a non-obvious way. Finally, we note that the connection between logarithmic spirals and Hadamard matrices has a faint precursor in the theory of Hadamard matrices constructed via circulant structures. Circulant matrices are those whose rows are cyclic shifts of a fixed sequence, and their spectral theory is governed by the DFT, a tool closely related to angular character sums. The Paley matrix Q is itself almost circulant. It is a back-circulant, meaning Qij depends only on Ji. The angular Fourier coefficients chi-m, p, of definition 5.5 are precisely the DFT coefficients of the Legendre sequence, 1p, 2p, p1p. The golden angle spiral introduces a non-uniform frequency weighting into this DFT, potentially revealing spectral features not visible in the standard analysis. Section 9. Open problems and future directions. We collect the principal open problems arising from this work. Open problem 9.1, Theoretical Foundation for SSPM. Prove, or disprove, that the SSPM gap predictor achieves 100% accuracy at tolerance τ equals 2.5 for all A primes, not merely those up to 10,000. Equivalently, does the inequality g(n) less than or equal to 2.5 hold for all n greater than or equal to 2? Open problem 9.2, Arithmetic significance of. Is the optimal growth rate interval set membership symbol 1.65, 1.75 related to any classical constant in analytic number theory, for instance, the Kramer constant, the twin prime constant, or the Mertens constant? Open problem 9.3, Sector residue equidistribution rate. Quantify the discrepancy of the sequence, the PNMOD4N4, 2n equals 1n as n infinity. Does the golden angle spiral achieve equidistribution at the same rate as a random angular sequence? Open problem 9.4, QR spiral separation at finite p. For which primes p and parameters phi, k, is the separation index delta p, phi, k maximized? Is there a pattern relating these maxima to the arithmetic structure of p, e.g., class number, discriminant of q, p? Open problem 9.5, Prime sparsity conjecture, quantitative form. Establish a quantitative version of conjecture 6.3, specifically, find constants C1, C2, 0 such that for all hard orders n greater than n0, e gamma n, C1 ln n, while e gamma n, and set membership symbol C, C2 ln n. Open problem 9.6, Three-dimensional generalizations. Do helical extensions of the SSPM, in which primes are embedded on a helix in R3 with golden angle azimuth, yield any improvement in gap prediction accuracy? and do they connect to higher dimensional Hadamard objects, such as complex Hadamard matrices, or mutually unbiased bases? Open problem 9.7, Constructive application. Can the spiral gap signature be used as a heuristic to guide the search for Hadamard matrices at hard orders? Specifically, does minimizing gamma, n, over a suitable family of perturbations of n, e.g., replacing n by nearby covered orders, accelerate the construction of approximate Hadamard matrices? References: C25A, Cattell. A Geometric Approach to Prime Number Prediction, the Spiral Prime Method. Unpublished Research Note, 2025. C25B, A, Cattell. Optimized Spiral Square Prime Method, Parameter Calibration, and 100% Accuracy on Primes to 10,000. Unpublished Research Note, 2025. CIA 36, H, Kramer. On the order of magnitude of the difference between consecutive prime numbers. Acta Arithmetica 2, 1936, 23-46. Dav 00, H, Davenport. Multiplicative Number Theory, 3rd ed. Graduate Texts in Mathematics 74. Springer, New York, 2000. Gra 95, A, Granville. Harold Kramer and the Distribution of Prime Numbers. Scandinavian Actuarial Journal 1995, 1, 1995, 12-28. Had 93, J, Hadamard. Resolution D1 Question Relative Auxiliary Determinants. Bulletin des Sciences Mathematics 17, 1893, 240-246. HL 23, G, H. Hardy and J, E. Littlewood. Some Problems of Partitio Numerorum, 3, on the expression of a number as a sum of primes. Acta Mathematica 44, 1923, 1-70. HW 78, A, Hedate and W, D, Wallace. Hadamard matrices and their applications. Annals of Statistics 6, 1978, 1184-1238. IK 04, H. Iwaniec and E. Kowalski. Analytic Number Theory. American Mathematical Society Colloquium Publications 53. AMS, Providence, RI, 2004. Gene 94, R. V. Gene. Phyllotaxis, a systemic study in plant morphogenesis. Cambridge University Press, 1994. PAL 33, R. E. A. C. Paley. On Orthogonal Matrices. Journal of Mathematics and Physics 12, 1933, 311-320. Rib 96, P. Ribbenboim. The New Book of Prime Number Records, 3rd ed. Springer Verlag, New York, 1996. SY 92, J. Sebery and M. Yamoda. Hadamard Matrices, Sequences, and Block Designs. In Contemporary Design Theory, a collection of surveys, ED.J. H. Dinitz and D. R. Stinson. Wiley, New York, 1992, pp 431-560. TUR 41, A. Turing. A Method for the Calculation of the Zeta Function. Proceedings of the London Mathematical Society 48, 2, 1943, 180-197. WE 16, H. Whale. Über die Gleichverteilung von Zahlen mod. 1. Mathematisch Annalen 77, 1916, 313-352. Scheer 18, M. Scheer. The existence of a Hadamard matrix of order 764. Bulletin of the Australian Mathematical Society 76, 2007, 317 to 319. 1. The precise statement of Paley type 2 involves the Kronecker product with a specific 2 by 2 matrix. We omit the full details for brevity and refer to HW78. Section 3.2.